we know those values only at some locations, so we cannot just tell that we get the derivative anywhere. We can get a good estimate of the derivative, which we have to substitute by differences. Again, remember, I have been talking about the calculation of first or second derivative earlier in last lecture, and just note that we have found out that there is a special, very nice case for calculating a very good estimate to a derivative, and that is the central difference. If you have the desire to get a derivative of a function with high precision and low computational cost, it is very nice if you have two values of the function that are half step upstairs and half step downstairs. I mean, the central notation for a derivative is f(x) is f(x) plus delta half minus f(x) minus delta half divided by delta. This, according to what we have already considered last lecture, is a very precise solution to the estimation of a derivative based on quadratic behavior of the function. So if there is the third derivative and any higher is 0, then we would get an exact value. And now this would be very nice if we could place the samples of electric strength so that we will be sampling those values at locations close to the sampling value to bx, but shifted half the space step. So in fact, what we will be doing is that we will have a mesh for values of, for example, magnetic field B. So I will have a mesh. I sample B x over here, and because I have a number of values, so I will have bx I j. Now this is the next value, which would be bx I j plus 1, and here I will have another value of b x I plus 1 j, and here there is the value of b x I j minus 1, and so on. So we have a mesh of values, let's say equidistantly sampled values of b. And we will also sample with the same discretization step in space also the values of electric field strength. But now we will do it in a wise manner. For example, in this picture we have coordinates, so let's have those coordinates over here. Let's have this like y, and this like z coordinate. If this is the true, and we need the derivatives of ey against z, so let us place the ey so that it encompasses the value of b, the location at which we need to count the derivative exactly. So let's say that we have to make the derivative against z of Ey. So let's place those 2 points at which we make the discretization of Ey over here, so that we have the same discretization step for Ey as for Bx, but we have shifted the cuts at which we take samples by 1/2 of the step. Now the same situation we would use for the remaining component, which is Ez. We should make Ez and the derivative should be against y. So we would sample Ez in those locations. And of course here and here. So we have the discretization grid, but we shift the discretization points, the sampling points, for each of the components, so that there is the situation that we can calculate, for example, the time derivative of B at a point where we make the sample of Bx, so that we always have those two neighboring points to use central differences. Now this is a hard task because we have altogether 6 equations. We have to complement this equation by the circulation of H. But anyway, if we do it, well, I don't know the proof that there are only 2 solutions to that, but there are 2 solutions that have been published that place on one grid box those discretization points for E and H, so that for any case those partial derivatives could be calculated as center point differences, which makes quite good estimation of the derivative value. Moreover, the idea extends also into time. Now I will again get the last paper, and remember, we had the Euler method and said, okay, that would be very nice if we make one step in the method, that is the estimation, if this was not x but t, so this would be time plus delta t. We will shift one step ahead in time, and it would be very nice if we knew the derivative of the function just in the middle. So in the t plus delta t divided by 2. This would be a very comfortable knowledge if we had it. And we can reach that. Just it is important to discretize those electric field values not only on a space-shifted grid, but also at the time-shifted grid, so that you would have discretized those values in different times. And you can achieve a set with which for any time derivative you would have the future values of electric field or magnetic field for those derivatives of electric field components. So you shift both in space and in time. Now this is only possible due to the fact that at the beginning of the computation you define the field as 0. Then the next value is also known and is also 0. So before you introduce any feeding to the structure, you know not only the value in the current time, but you know also the future value before you change it. So you can start this calculation with knowledge of field in different times. And the knowledge is forced, it's 0. Now, in fact, you divide field values into two groups. One is discretized at t, t plus delta t, t plus 2 delta t. The other is discretized half step in time shifted. So t plus half delta t, t plus 3 halves of delta t, and so on. And now, in order to get the next estimate of this value, for example, for us that was the bx, you use the future value 1/2 time step ahead in time of electric field. You know it because it is discretized that way. So you recalculate the magnetic field 1 time step ahead. Now you have to recalculate the electric field, those values you use for the magnetic field. And you can do that in the same manner because you already know 1/2 step into the future the values of the magnetic field. So you would then recalculate the other group, let's say in blue, and then you can again recalculate the magnetic field because you already know the future electric field. Now this algorithm has its name. It has a very nice name in English, although there is not a corresponding name in Czech. So in English this is called a leapfrog algorithm. It somehow resembles a frog that is jumping, if you have seen it. It looks like this a little bit. So this is a leapfrog algorithm. And there is one important point about this algorithm. It is stable only for short time steps. And there is a special equation that tells you the maximum time step at which this is stable. Now, we will learn the equation later, but the important point is the way how we make the calculation. So 3 important ideas. We cut the space by a discretization grid. For simplicity at the beginning, let us consider that the grid is equidistant and the steps are the same in all 3 dimensions. So you make a cut in x, a set of cuts in y, a set of cuts in z. And you make shifted grids, 1/2 step shifted grids for field components, and place them so that for any derivative calculation you have 2 neighbors half step distant. Then you also make a time discretization of all the values, and again you divide them into 2 groups so that those groups depend one on the other and are again 1/2 time step shifted. Then you have an algorithm which can upgrade all the values in the net, all discretized values, by 1 time step into the future, and you always have neighbors both in space and in time organized so that you can use central differences approach, and that therefore get your computation quite accurate with low computational cost. Now just let us consider how computer consuming is this upgrade. So let's say that we would like to find how computer intensive is this calculation. Instead of having a derivative of ey against z, we would have, let's switch again the paper ahead. So we have the grid here, and for the notation we have put here, let us put down this equation exactly. Now what we miss still in the picture is so this distance would be delta x, and this distance is the step, discretization step in y, and let us make it again delta x to get simpler equations. So now let us find how an update formula for bx in the central location looks like. So we first have to calculate the time derivative. The time derivative would be achieved in both cases like the next value minus the previous value divided by the time step. That's the central difference. And we will have the time step and space step, the same one for both derivatives. That makes no sense to calculate that ratio each time when doing the calculations. You will just at the beginning make that for all the points in the net and then have one constant. So we will introduce a constant c, which is the time step divided by the space step. That would make no sense to repeat this calculation a billion times. So we first make this calculation before we start the iterative process. Now we can put down that bx, and I will again mark next, is equivalent to bx plus, and we will have c times. So first let's handle the derivative of ey against z. That is ey I plus 1 j minus ey I j. I will make more brackets, which will not make more operations, but to make this clear. Now I would put the rest of the big bracket, that is the derivative against z. And I would instantly put in it in the manner that there will not be the minus but plus. So I will have plus ez. I should take, I had ey, and I have the other discretized over here. So I would have ez I j minus e z I j plus 1. So this was the other derivative and the end of the bracket. Now let us calculate the number of operations we have to do to update one point. So we have one 2, 3, 4 additions. Four additions. Again, 1, 2, this together 3, and there is another addition, 4 additions, and 1 multiplication. So with the expense of 4 additions and 1 multiplication, we can update one net value one step in time ahead. Now, a good news, we will never need the old value for the process. So we can store the newly obtained value to the same location. We can forget bx and substitute it by the next value of bx. And on the expense of 4 additions and 1 multiplication, we can update one net value, which means that on your PC or on your mobile phone, you would be able to handle, let's say, 1 million of net values in a second. With a well-organized and a good computer, you would be able to handle some 20 millions of net values in a second. Now the bad news is that for each space location you would have 5 net values, ex, ey, ez, and for example bx, by, bz, or hx, hy, hz. So 3 electric and 3 magnetic components. So that is 6 times lower. And then the other bad news is that you would have to cut the area with a set of fine cuts that produces a number of values, and you will have to make a number of small steps in time not to lose convergence. But on the other hand, the algorithm is very easy to program, and therefore it is quite fast. And this makes this method, finite difference time domain, the number one method as to today's solution of electromagnetic field in closed volumes. I will just comment on that. So that's not the number one solution for antenna problems, but a number one solution for electric circuit, definitely. Now please, your questions.
Can I ask you about the reference implementation of the successive over relaxation problem, about how